Right. So today topic is, as we said, it's about properties of pure substances, and we will learn how to find the properties of pure substances. Mainly, we're gonna find how to find the property of the water as liquid, the water as vapor, and also other pure substance like one of the refrigerant substance. So will also show you how to represent the properties on the TV axis diagram, and also pressure volume diagram, and some other new definitions related to these diagrams, such as the latent heat. So, so what's the pure substance? Before we go to the tables, we need to know the definition of pure substance, which is a substance that has fixed chemical composition during any process. So let's say if for the water, it's H2O, and whether it's liquid or it is gas or solid, it had the same composition, doesn't change. So we call it pure substance. And sometimes even a mixture of various chemical elements or compounds, sometimes we call it pure substance, such as air, because air, even the air, let's say when you have air heated to any temperature, still have the same composition, right? So, and we have mainly three phases. Of course, these are the phases that we deal with. We have solid phase, and we have liquid phase, and we have gas phase. And you can see in the figure below the structure of molecules in each phase. In the solid, you can see that the molecules are uniformly distributed, while in the liquid it's a bit scattering, and the gas is very randomly scattered. So each one have a different structure. So the atoms, as you can see in the solid, uniformly distributed, while in the liquid start to move randomly from each other, and of course in gas, if you find it it's very random structure. So now phase change process of pure substance. If we, let's say, imagine that we have water, for example, stage 1 here, we have water in a cylinder, and we put on the top of the water this piston. So there's a piston on the top of the water, and we start to provide heat, add heat from the lower part. So the water at the beginning is at 1 atmosphere and 20 Celsius. So when you start heat the water, then or the temperature start to rise, and up to, let's say, temperature 100. And as you know, when we reach to 100 at atmospheric pressure, the water start to boil, right? So this is like the starting point for changing the phase from liquid to gas, or liquid to vapor stage or phase. So as we keep adding heat in stage 3, as we keep adding heat, the temperature will stay constant, keep constant, because we didn't change the whole water to steam. Part of the cylinder is vapor, and the other part still liquid. So while we are adding heat more and more to the cylinder, we can see that more water, more liquid start to change phase to gas or to vapor phase until we reach completely gas or completely vapor in stage 4. So for stage 4, while we keep adding heat to the cylinder, we find that at the point 100 Celsius, we find the whole liquid change to vapor. So these 2 points, number 3 and number 4, are the beginning. 3 is the beginning of vaporization. And number 4, end of vaporization. Okay. After that, because we have all liquid or all water has been changed or has been changed to vapor. After that, if we start to add any extra heat to the vapor, we will move to the stage 5, which is, we call it a stage where we have superheated steam or superheated vapor. So we call it superheated steam because it's no more at boiling temperature. As you can see here, the temperature start to rise to higher than 100. So it comes to up to, let's say, 300 Celsius. So these are the stages from 1 to 5, represents phase change process of water. And we can plot these on a diagram, let's say, pressure volume diagram or temperature volume diagram, to find out the actual process or the phase change process on the diagram. So we'll come to this now. So we'll show you this here. This is the y-axis is temperature. The x-axis is specific volume. So specific volume here, it's cubic meter per kilogram. Okay, and y-axis is temperature. So as you can see, if you look to the stage 1, we were here. This is stage 1. At this point, we start to heat the water, so you can see that temperature start to rise up to the 100. So the 100 here is boiling temperature. Okay, or they call it saturation temperature. So when we say saturation temperature from now on, it means the boiling temperature at a certain pressure. Okay, because in all these cases, we have always the atmosphere. We don't change the pressure. So the pressure here are on fixed. So as you can see here, the line represents P1 atmosphere or 1 bar or 100 kilopascal, all of them same. Okay, so the red line here represents the constant pressure line, and during this constant pressure line we are increasing the heat. So as you can see, as we mentioned, stage 2 we have start the boiling, and then after stage 2, for example stage 3, it's somewhere in the middle. So because part of it gas or vapor, and the other part is liquid, still liquid. So we are in a 2-phase region now. Okay, but the temperature is the same because we still didn't change the liquid completely to vapor. So because of this, the temperature will be constant. So we keep adding the heat until we reach number 4. So 4 represents point of the end of vaporization. So after that, any extra heat will increase the temperature, as you can see. At 0.5, temperature is 300. Okay, so this is the process of phase change for a pure substance, which is the water. Any question in this regard? Okay, so as we mentioned here, all these are the steps we followed during the heating process. And then we have, in each step, we have certain, we have change, a phase change taking place at 2, 3, and 4. Okay. Right.
But in this, sorry,
Yeah.
in that phase changing process, the volume remain constant?
No, because as you can see, for example, at 1, we have volume here, V1. At 2, we have different V. At 3, we have different V, right? So at each point, the volume also change. So the volume and the temperature change. So up to 5, we still have change in volume, specific volume. So in every step, we have change in volume.
So in that arrangement, there is a plate on top of water, right? That's a plate.
Yes, like we call it a piston or a disc on the top of the water, correct? And this is just to contain the amount of water inside the cylinder, so that otherwise it's going to escape, right? Okay. So we will lose the mass. So to keep the mass inside the cylinder, we put that disc or that piston at the top, and the pressure is always constant because it's atmospheric pressure. We don't put any other weight on the top of it. So we have always P atmosphere at the top. Mm-hmm. Yeah. Clear?
And for the superheated steam, like if I want to have a superheated steam, should I go till 300 or it can start beyond 250 or something?
Yeah, if you start beyond this point, it will be superheated steam.
Yeah.
So beyond the 100, it's going to be superheated steam. So there's no chance of liquid at all. It's purely heat. It's purely vapor phase or gas phase. Okay. All right. So and just to give you like information or idea about the change in saturation temperature, which is the boiling temperature. We said that when we say saturation, it means boiling temperature at a certain pressure. So the change in saturation temperature or boiling temperature, as we said, changes with the atmospheric pressure. So if you look to this graph, the first one, this one, you can see that at, for example, P atmosphere 100, which is the sea level P atmosphere. So 100, the temperature here is, saturation temperature is how much? You can see
100,
which is the one that we know. It's 100 at atmospheric pressure, sea level atmospheric pressure. The boiling temperature of water is 100. Okay. Now, if you go above sea level, what will happen? Look to this graph. This is the sea level here. When we have 0 sea level, if I go, for example, to a mountain, the mountain height is, for example, 2,000 meters. What will happen to the pressure?
Drop.
It will decrease.
Decrease, correct. So if you go to, say, for a mountain and go to a mountain, you'll find that the atmospheric pressure decrease. So if the atmospheric pressure decreases, what will happen to the boiling temperature? If I put it, let's say here, 80. What will happen to boiling temperature?
Will it decrease?
Also decrease, correct. Okay, so with the decrease of atmospheric pressure, the boiling or saturation temperature will decrease also. So for example, if you are making tea at sea level, you need to keep heating the jar or the pot, heat it until, for example, to reach 100 Celsius. But if you want to go, when you go to the mountain, you need less energy because the boiling temperature will be less, will be 80, not 100. So you will consume less energy because you don't reach 100 Celsius, you reach 80 Celsius, you find the water start to boil. Okay.
And, yeah, so in our tutorial last week,
yeah,
the teacher, he gave us an example of saying the Dead Sea being lower in elevation than sea level. So the evaporation rate is higher.
Correct. And so, the boiling temperature will be higher.
Yeah, but isn't the pressure higher there then?
Yeah, that's right. The pressure will be higher. And you can look here, if you go higher.
Oh, pressure, right, yeah. But he was saying that, you know, there's more evaporation at the Dead Sea, like, and that we float more. But I found that confusing because, you know, my understanding is, as we rise.
No, it's because not the reason for that, definitely. Not because the pressure, but
density.
The water, and also it's salty water, so it's not so many factors.
Right. Yeah, I was a bit confused. I was like, you know, in space and on Mars where there's no atmosphere, like our blood will boil.
No, that's because, for example, in the space you don't have atmospheric envelope.
Indeed, yeah. Same with Mars, with like a very low atmosphere.
So you have direct solar radiation. You don't, like, you know, the solar radiation doesn't scatter in the atmosphere. So you don't have dust, you don't have water vapor in the atmosphere. So it's just empty, clear. So you reach, like, you know, you receive radiation. You receive more radiation than when you have atmosphere around the.
Sure, but like the radiation will kill you. But, you know, does that have anything to do with your, like,
the pressure,
the boiling of liquids?
No, because you know, with let's say, if you say, like, talking about Mars, there is no atmosphere, and therefore there is no atmospheric pressure.
Yeah.
Correct. So what makes the pressure actually here?
Our atmosphere.
Let's say on Earth, it's our atmosphere. Like, you go, for example, you can model the atmosphere by going underwater. So the deeper you go, the more pressure you have, because the column of the water will be higher.
Yeah.
So with this column of water exerts pressure on your body. So even if you go, so that's for the water. If you go outside the water, what makes the pressure on your body is the atmosphere. So the column of air on the top of your body, this is what makes the atmosphere, what makes the pressure. But because it's air, the density of air much lower than the water, you don't feel it. Yeah, but if you go, let's say, in the ocean, let's say, for example, 100 meter down or 200 meter, you can't live there without proper suit that you need to wear, and also you need pressure, you need oxygen to have with you, like, otherwise this is like what's going to happen to you, like your cells will be destroyed. So with the pressure, of course, whenever you have atmosphere, you have pressure, and with the pressure, then you look at here, the more pressure you have, the more the boiling temperature will be, of course, higher. Yeah. But if talking, say, for example, Mars, for example, 0 here, but this doesn't mean, like, only this factor affecting, because we said radiation also another factor that.
Right. Yeah. Sorry, I was just a bit confused about his analogy of the Dead Sea last week. I should have asked him, but that's all right. Sorry to distract.
Yeah. No, it's okay. Why? Good to discuss this. Yeah. Okay. So this is like what we said here. We have two definitions: saturation temperature. We know that what saturation temperature. It's at a given pressure, the temperature at which pure substance change phase. So from liquid, for example, to gas. Or backward from gas to liquid, condensation, which is same that we have same temperature, which is the saturation temperature. So we call it saturation temperature at constant pressure. Same thing, we have saturation pressure, which is at given temperature, the pressure at which the substance start to change phase, same thing. So either we fix the temperature, we find the pressure that change the phase, or we fix the pressure, we find the temperature that change the phase. Okay, we'll come to this more, explain it more and more. Just want to see the time. Okay, so these are like, this table just give you an idea, the change of boiling temperature with the elevation. So as you can see here, the higher elevation need lower boiling temperature. Okay, because we said pressure will be lower, as you can see in this column. Okay, and saturation pressure against temperature. So for each temperature, we have saturation pressure, or you can say at this pressure, we have this boiling temperature. Same thing. So until, let's say, we reach to this pressure, which is almost the atmosphere, this is where we have boiling at 100. Okay. So, and that's why, in the pressure vessel or pressure pot, you can see why we use the pressure vessel. Because when you have pressure vessel, you will have higher temperature, higher boiling temperature. So if you have higher boiling temperature, the food will be cooked faster. Correct? If you leave it to the atmosphere, just open vessel and try to cook in the open vessel, you will have this temperature here, 100 Celsius. While if it's closed under pressure, then this is the cooking temperature. So we'll have the food will be cooked faster. Yeah. And now we have the also definition of latent heat. And latent heat is the amount of energy observed or released during phase change. So for example, if I have gas here in this figure, I want to change it to liquid, then I need to remove energy from the gas. And we call this condensation, because I want to condense the gas, so I need to remove energy from the gas to make it liquid. So in this case, this process also, which is the condensation process, in this process, we need to know what's the amount of heat to be removed from gas. How to know this? By knowing the latent heat of the gas or the pure substance at a certain pressure. So for example, for water, if I have, for example, water vapor at 100 Celsius, I want to change it, or want to change the phase to liquid, completely liquid. I know that I need to remove the latent heat of condensation or latent heat of vaporization. which is given in tables. So we'll show you the tables very soon, but this is what you need to know. The same thing, other way around, if I want to change the water to gas, so we call this vaporization process. And how much heat we need for this process? It's the same amount of condensation. So the same amount of heat removed from the gas, which is the latent heat. So latent heat of this process, we call it, for example, latent heat of fusion, the amount of energy observed during melting. This is for solid. So for solid, if I have ice, for the water, if I have solid water, which is ice, I want to change it to liquid, then we call it latent heat of fusion, the amount of energy observed during melting, or other way around, the amount of energy required to remove from liquid to change it to ice, from water to ice, then this is the amount of I need to remove. This process, change the water to ice, to solid. Either way, changing from liquid to solid or from solid to liquid, we call it latent heat of fusion. Okay, so just to reach the freezing point. Okay, so we mentioned this latent heat of vaporization. So now we know the difference between latent heat of fusion and latent heat of vaporization. Okay, any question? All right, and there are so many applications for the latent heat. They use like some of these in medical equipments. For example, when they want to store a certain element under, or a certain object under very low temperature, minus, for example, 100, minus 50, minus, here let's say, for this case, minus 196, because depends on, again, depends on the substance. So for, let's say, nitrogen, if the nitrogen, liquid nitrogen, if we want to release it to the atmosphere, 1 atmosphere, start to boil at 1 atmosphere. So it has very low temperature, and the boiling temperature is minus 196. So everything, if you put this liquid nitrogen, as you see here in this figure, if you put it inside a container, and then there is a chamber inside the container here, we store whatever you want to store here. So if this start to, if you open it to the atmosphere and start to evaporate, the evaporation temperature is minus 196, which means that everything inside the chamber also will be minus 196, because we said this is a phase change process. So we have two-phase region. In the two-phase region, the temperature of all components or all phases, whether liquid or gas, will have the same temperature. So if the gas boiling temperature of the gas is minus, then means the temperature of the liquid, saturated liquid, also minus 196. So everything inside the content, this box or this chamber will be under 0. Okay, so this is one of the application. There are other applications. Also, they call it vacuum.
I have a question.
Yes.
Okay, so if the chamber is not open and the liquid nitrogen is like isolated inside, so what's the temperature then?
No, because if it's closed, then there's no, because there's no vaporization. There will be no because it's going to be under pressure. The pressure is not atmospheric pressure anymore. When you open it here,
then it starts to boil, yeah.
Yeah.
But before that, what's the temperature if I don't open?
So it depends how, like, what's the pressure inside?
Oh, okay, yeah. that
Yeah.
makes sense. Mm.
So the more pressure, make it liquid. Okay, less pressure, then you will change it to vapor.
Okay, cool. Yeah.
So how
Okay.
this process is beneficial in medical field? I didn't understand. Actually,
No,
it
but
is
this is not like a actual device, but just to show you that because in actual device there is a kind of, for example, a complete system. For example, there's a compressor and then compressing the pumping or compressing the nitrogen inside the chamber, and then to make it higher pressure, and then suddenly they open. There is such kind of, they call it a nozzle. A nozzle will expand suddenly and then allow the nitrogen to evaporate because of the change of the shape of the pipe, let's say from small diameter to bigger diameter. So this will make the pressure lower. So this will cause evaporation of the nitrogen, and then they keep doing this as a circle, like like the air conditioning system or
refrigerator.
refrigerator, yeah. But for this figure, just to show you that if you have gas under pressure, for example, nitrogen, and suddenly open it to the atmosphere, lower pressure, this lower pressure will allow the nitrogen to evaporate. And once it starts to evaporate, we know that evaporation temperature of nitrogen is minus 196. So minus 196 means that you are under freezing temperature. Yeah.
All right.
Clear?
Yeah.
But this is like, not a complete system, just like give you an idea what's going to happen. Yeah. Right. So now we'll if we, as we mentioned before, we can plot the change of the phase change process. We can plot it on either constant pressure lines or constant temperature lines. Yeah. So if I say now, I go again to this graph, the TV diagram, and I start to plot the change of, for example, specific volume with the temperature at each constant pressure. So let's say I fix the pressure and then start to heat the vessel or the cylinder that we show you before. So at this pressure, we can see that this is the process, or this is the line that the phase change will follow. Then I increase the pressure on the cylinder or on the disc. So maybe if I can show you, yeah, maybe here, I'll draw it here. So if I do this again, this is the disc or the the piston I mentioned before. And here like water. And we put, for example, first line here, this line, without any weight on the top of the disc. Okay, so this is, for example, case one. I take the only atmospheric pressure, the atmosphere, and start to heat Q underneath. And I'll find out this is the line that the phase change will follow at this pressure. Now, second test, I take higher pressure. So what should I do? I should put more weight here. I put mass here on the top of the disc, which is equivalent to this pressure, and start to do the heating again. And we'll find out this is the line that the phase change will follow, and so on. and keep adding more and more weight on the top of the disk until I reach this pressure. Okay, and we call this pressure critical point pressure. Okay, so why we are doing this now, if you have a look to the graph here, the first pressure line has this amount of latent heat. You can see, because we said the starting boiling point here, that we change some of the water to vapor until we reach to the other side where we change the whole water to vapor. Between them, we call it latent heat, correct? So this distance represents the latent heat of vaporization. And as you can see, the more pressure you have, the less latent heat you need. Correct? Until we reach to the point where we have a sudden change from liquid to vapor at pressure 22.06 megapascal. Okay, and we call this the critical point. So the critical point defined as the point at which the saturated liquid and saturated gas are identical, which means that saturated liquid and saturated gas volume is the same, because this is the sudden change. While in the other cases before critical point, we have saturated fluid or liquid, and we have volume, and we have saturated gas volume or vapor volume. Saturated liquid here and saturated vapor volume. They are different, but when we go toward the critical point, then both of them will be identical. Both volume will be the same. Okay. So I don't know if this is clear for you, everyone.
Yep, sir.
I think we'll, with the some example you'll gonna
the
find.
critical point, is it different for different materials? Like
Yeah,
substance?
definitely.
Okay.
This is not only like not for all materials. It's not all for substance. Only for water. We're talking now about the water.
Yeah,
But for each
liquid, yeah.
Yeah, for each substance have different values, of course. Yeah, but the behavior will be the same. So you take any other substance to have the same behavior.
Yeah.
Like with the higher pressure, we have less latent heat. With the lower pressure, you have more latent heat. Okay.
Mm-hmm.
And we said that this is for pressure. Okay. So what is for pressure? At constant pressure. Okay. Now we can do the same thing, but for constant temperature. So we will not take too long on this, because basically, or actually we use the constant pressure line more than constant temperature line. It's more like, it's easy to understand, because sometimes we deal with the pressure more than constant we deal with constant pressure more than we deal with constant temperature. Okay, so but what I need from this, from the whole thing is I need to find out the new property, enthalpy. So enthalpy, as you can see here, it has two components. It has U, which is the internal energy, the plus the pressure multiplied by specific volume component. Okay, and the unit for enthalpy, same as for internal energy, it's kilojoule per kilogram. Okay, this is per unit kilogram. If it's total energy or total enthalpy, then it's only kilojoule. Right. So this is like a new property that we're going to use a lot in thermodynamics, and it will be given in tables as well for each pressure. But to understand the property tables, there are a few things we need to, or few properties we need to understand. The specific volume has three types. We have specific volume at saturated liquid. You remember the graph. This is constant pressure graph. And we said that we have these 2 points. This one represents VF liquid. We call it liquid, saturated liquid, specific volume. And this one, when the end of vaporization, we call it VG, saturated vapor. Okay, so specific volume of saturated vapor. So these are two values given in tables. So when you have, if you have a pressure, you take the pressure, go to the tables, and at this pressure you can find VF and VG. All right, and the difference between them, we call it VFG, which is following this equation. Of course, it's V, the gas, minus the liquid. Specific volume of the gas minus specific volume of the liquid. We call it VFG. Okay, same thing with the enthalpy. The enthalpy has also HF at this point. So I know the enthalpy HF at this point, and also I can find the enthalpy at the saturated vapor at this point. So these also given in tables at each pressure line. Okay, so rather than we have a graph and go to the graph and find where is the enthalpy, we go to the tables, make it easier. So at each pressure in the tables, you can find HF, HG. You can find also VF, VG, and also you can find out the T saturation, because at this pressure we know what's the T saturation. Okay, these actually the main component of, or the main properties given in the pure substance tables. Okay, now the tables are given in the in views. If you wanted to see it there, these are the number of tables. I don't know. Do you have, all of you have now access to the to views, or I mean, do you have a proper PC or laptop? Because if you are using your mobile phone, it's very hard to.
Yeah, we have.
Do you have the, okay, is it
Yes, sir, we
okay
have
for
the
you?
laptop.
Sorry, Imad?
Yes, sir, we have the laptop.
Yeah, so is it possible for you now to follow me? Like I'm gonna go to the website, to the views, and show you where is these tables. Can you please download them, download these two at least, or these three, because these are for the water. So it's there. So I'll show you where to find these tables, and you can download it to your desktop, so we can do some practices. Okay, so let me show you. Okay. Can you see this page? If you go to the learning material at the top, learning zone, everyone is there.
Yep.
Okay, so I click on learning material. can find here tables and figures. Yeah. Click on that one. And you will find these tables. So I want from you table A4, A5. And you can maybe download this one. This will take it later on. But these two tables, we're going to do some practice on them. Can you please either open them or download them to your desktop? Everyone can access these. Anyone can't do it? Can't. So all of you okay? All good? Okay.
Yes, sir.
All right. Okay, so we'll go back to the slides. Actually, let me show you here. This is A4. This is how it looks like. All right. So as you can see here, the table, the first column of the table represents temperature. See this column? These are the temperature. If you go downward, you'll have higher temperature. So against each temperature, you find second column, which is the pressure. So what does this mean? If I take, for example, 25, of course, this is for water only. We call it saturated water table, saturated water temperature table. Why we call it temperature table? Because the first column is temperature. Okay, so what do you need to do here? If you have temperature in the question, immediately you know that I need to go to the temperature table, not pressure. If you have pressure, then you say, okay, I need to go to the pressure table. So if the temperature table, the first column here is temperature. So for example, if I have 25 degree, 25 Celsius, at this temperature, if I want to make the water boil, if I want to make it boil, then I have to reduce the pressure up to this pressure. Did you get me? Yeah? Did you get what I mean?
All right, so just repeat it.
If I want to, this temperature actually, we call it saturation temperature. All right? And or boiling temperature of the water. If I want the water to be boiled at 25 Celsius, I need to reduce the pressure to this point, 3.16 kilopascal. It's very low. Yeah?
Mm-hmm.
So now, if I go further down to 60, for example, this is the new saturation temperature or new boiling temperature. Yeah. At this boiling temperature, what do you find? What's the pressure? Higher or lower?
Higher.
Higher. So the more boiling temperature I want, I need to have higher pressure. Of course, when I reach to atmospheric pressure, let me clear this, go further down. Before atmosphere, you can see here, this is 95, which is close to 100. And you can see the pressure coming closer to the atmosphere. Yeah.
What's atmosphere? 106 or something, or?
Yeah, 101.
101.
Yeah. Okay, so now I will go to the next page. Oh, sorry, okay, this page, good, it's there. So this page can see 100 T saturation 100. Which means that if I want to boil the water at 100 Celsius, I must be at sea level pressure, 101. Okay. So for each temperature, this is the pressure. We call this T saturation, and this is also P saturation. Okay, so both of them at saturation point. right? Question before, yeah. Okay, so now if you look to the, let's take this pressure. Okay, if you go along the row, this row, you'll find all the properties at this saturation temperature or at this saturation pressure. Okay, so if you look at the top here, we have VF, we have VG, right? So specific volume of saturated liquid, specific volume of saturated vapor, and also we have saturated internal energy of saturated liquid and saturated vapor. Also, we have enthalpy. We just mentioned this, enthalpy of saturated liquid and enthalpy of saturated vapor. And the latent heat, this is what we call latent heat, HFG, the difference between HG and HF, latent heat of vaporization. Okay. So now if I want to ask, for example, let's do it now. Let me ask a question. I'll clear it. I will take, for example, I'll take 110. Okay. So what's the saturation temperature at 110?
Saturation temperature is 110 itself.
Yeah, 110. Okay. And what's saturation pressure?
143.38.
Correct. What's the latent heat of vaporization at 110?
Latent heat, right?
222 9.7.
Yes. So if you go down here at this column, 2229.7. Okay, kilojoule per kilogram. The unit's not showing here, but maybe at the top we can find the units. So it's all these are in kilojoule per kilogram. Even the enthalpy here, sorry, internal energy. Okay. Okay.
Yep.
Right. So that's actually we call the saturation temperature table. Now, something similar, they put this the other way around. They take this, put it first column, but they put it round figure for the pressure. They don't take, let's make it like these ones, 0.6 or 1.22, and they just take it as a round figure. Against each pressure, they put what's the temperature. So exactly the same, you'll find out very soon, but the values rounded to the correct value. There is no fractions. Okay, for the first column. Okay, well, we'll check this now. So this is the saturated water temperature table. The other one is this is the, if you look at it, to the top here, saturated water, but pressure table. Pressure table. So it means that the first column is pressure. And you can see here, you don't have only one digit, you don't have more digits than one. So you have 1, 1.5, 2, 2.5, and so on. the pressure value is rounded to the first digit only. And after that, actually, it comes to no digits at all. But against each pressure, you find what's the saturation temperature. So the other way around. So if, let's say, for example, if I want to know the atmospheric pressure, what's the boiling temperature? Of course, should be 100. Let's see, let's check this, if it's correct or not. So if I go down and reach to the boiling, to the pressure 101, which is very close to the atmosphere, what's the desaturation? It's 99.97, which is almost 100. Yeah. So that's actually what we call the pressure table. And again, if you know the pressure here, you can find all other properties at this pressure, exactly the same. And if you look to the, for example, to the latent heat, it's almost the same. When we use the last table, the one table before, it's the same thing, 2256.5. That one maybe less, small fraction different because of the difference in saturation and fraction of the saturation temperature. Any question? Do you think it's hard or easy to?
No, it's fine. Is it are both considered correct?
Yeah, of course. Yeah, but for example, you will not, let's say, for example, most likely in the questions you will get a round figure. So for example, you get 100 or 150. So for this temperature, for this pressure, you can easily find the temperature, saturation temperature, and you find also all other properties. Yeah, but this is just to show you that we are very close. They are very close to each other. Both tables very close to each other. Either pressure table or temperature table, they give you the same result at the end. And let's say in the design or in the analysis of any system, we don't worry too much about the fractions, 0.5 kilojoule or 0.6 or 0.1, because when we say a flow of, let's say, steam, we're talking about like, big amount of steam flowing. So not only, let's say, 1 gram or 2 gram of steam in a power plant, right? So we say, let's say, a boiler of 200 or 500 kilogram of water or 1,000 kilogram of water. So when you have big values, the small fraction doesn't make difference in big values because it's very minor error. That's like almost negligible. Yeah. Okay. So I think maybe we need to do practice because now time is, almost more than 1 hour. Let me skip this. So any question before we move to the Kahoot? Maybe the Kahoot is the best thing to do with this. Any question?
So one question for the enthalpy and entropy. Is that something like the properties, is that physical properties, like something that we can see or feel, or this happens inside the material or the substance?
The enthalpy.
Like, for example, the pressure we can feel, or maybe, you can say there is a high pressure, but enthalpy, can you see or feel that, okay, it is on high enthalpy? No, because you can't feel the temperature. Okay, we say like last time we said we have sensible heat and we have latent heat. So it's the thing that you can sense. This is where you can see this is the temperature of, for example, the liquid. But the latent heat, you can't sense it. So, but it is because of the change in phase. Okay. So yeah, this is like kind of energy per kilogram. So this is different from temperature, something that you can sense. Sure, thanks.
Yeah.
And is the definition of enthalpy, is it the opposite of entropy?
No, entropy, I'll come to that. Actually, this is more complicated thing. The entropy, just forget about this now. this side of the table. You don't need it now. We'll come to this when we reach the second law of thermodynamics. So entropy actually is the measure of the randomness of molecules.
Chaos and
The chaos, exactly. So the more entropy means that you have higher quality energy because of the randomness. Contain a lot of energy. You know that this amount, and it's quality, not only quantity. It's high quality energy. So the higher entropy, it means you have higher quality energy, not only quantity but quality. We'll come to this. Yeah, but just for the time being, just forget this part of the table. You don't need it. Focus on these parts.
all right, thanks.
Yeah. Okay. Yeah, let's go to the, if we have anything else here. Yeah, these are, yeah, I think we already talked about this comprehensively. We don't need to go to the table. This is like, slides showing the tables, and I already showed you these tables. But just one more thing I want to mention here before we go to Kahoot. There are also in the, we said in the phase change region, again, I'll plot this here. So we said this is pressure. So these points, we said this is VF, this is VG, because this is saturation liquid, specific volume, and saturation vapor liquid volume, specific volume. And the mass, if I take any point here, I want to find out the total, call it T point. T, if I want to take the mass here, the mass of this substance consists of mass of liquid plus mass of vapor, because it's in the middle or somewhere between the vapor and liquid. So it's two-phase region. So it should contain both masses, the mass of liquid and mass of vapor. So they give simple for liquid MF in tables, and simple for gas or vapor, they give it G. So M total is equal to MF plus MG. Same thing for the volume. The volume, total volume, is the liquid volume plus gas volume. All right. Now, why do I need this? Because from this I can find a property important for the two-phase region, which is the quality. Because you know that we mentioned again in two-phase region, the temperature is constant, doesn't change. So if I want to, for example, find out the property of this point, I can't say this VF because the VF is here, and I can't say this one is VG because VG is at this point. It's somewhere in between. So I can use only T saturation to know the, for example, VT, I'll call it, right? Because it's somewhere in between. So I need another property to describe this point. This property, call it quality, and which relates to the amount of mass, the mass of gas to total mass of the mixture. Okay, so if I know the quality with the temperature, it's easy to find other properties of this point, VT. Okay, so the quality, if you can see, the X is the mass of the gas divided by the total mass of the mixture, gas and liquid. Okay, so I use this quality, as I mentioned, to find the specific volume or internal energy or enthalpy somewhere in between into the two-phase region. Okay, as I mentioned, if I want to choose any point, in the two-phase region. I call it, for example, average. This point, it's average between VF and VG. Okay, if I want to find this V average, then I just follow one of these equations. But I need to know what's X. So most likely in the examples, you will be given value of X, or the other way around. You have the mass of gas, mass of the total mass, you can find X, and from X you can find the other properties at average point of two-phase region. Okay? Any question?
No, sir.
Okay. All right, so let's go then for the example. Because we need to relax a little bit. I know that you get tired, so let's go to the Kahoot, have some interaction. All of you know how to use the Kahoot now, I think, right? So just go to the okay, you can open the Kahoot, please. So we'll share with you the screen now. It's about steam table. So if you have the table in front of you, you can make, like, you know, on the screen, two sides. One side put the tables, the other side you use the Kahoot screen. Or I know that maybe you didn't print it yet, but I prefer that for the quiz. It's better for you to print these tables, at least table 4 and table 5, because it's easy for you to search for the property on the paper. So if you have it on the screen and you have two screens on your computer, and it's going to be like confusing for you to move from this to that one, unless you have more than one screen at home. But it's much better if you have it printed. So if you have hard copy with you, it's easier for you to find the values. You just need to have a pencil and with a ruler, and you can find out the values anywhere. Okay, so this is the quiz gonna start now. So this is the code. The pen, please, can you enter it?
So
I
do
will
you
take-
do individually?
Sorry?
Do you want us to do individually?
No. I will open it now. We can see it.
All right.
Yeah, I will control it. You need to enter your name, because I use this name for attendance. So please use the same name in your sheet. Everyone is in? Let me see. 1, 2, 3, 4, 5, 6. We have 6 students.
So I don't know how to get in.
Didn't you haven't you done it last week?
No.
Okay, so write Kahoot on your
Okay.
search engine, And then there will be Kahoot, I think for students, or just click on that one and they ask you to, you don't need to download it. That's for Dean.
Yeah,
you get
yeah,
it?
I'm getting there.
Yeah.
Play
So
Kahoot.
yeah, and then join. Just click on join, or and they'll ask you.
Asking for the pin.
Yeah, this is the pin. Can you see the pin at the top here? 84666476.
86.
So everyone using their PC, right? Not a mobile phone.
8466.
Yeah, imagine. Yeah, good. So now everyone in, we'll start. So you need to make your tables, open table 4 and 5, make it ready. Everyone downloaded the tables to the desktop?
Yes, sir.
Just give me a moment, I'll print it up.
Yeah, either print it or download it to the desktop so it can be handy for you. Can easily access it. Done? Okay. So gonna start it now.
Yes, so we can start.
All good? Okay, so gonna start this now. What's the saturation pressure of water at 45? So look at the table and find out saturation pressure at 45 Celsius. And as I told you, because you have 45 here, you just need to go to the first column. Made a mistake?
No, I just don't like the format. I can't see the question on my screen.
Yeah.
Okay, no problem. You still have chance to win. It's first question.
I can't see the question on the screen.
You can't see the question.
The
Yeah,
question
only on the
will be
view
shared on
screen.
the Zoom screen.
Yeah, the question in the Zoom screen. Well, that's my point. You're gonna have two screens here.
It's better if you use Kahoot from your mobile and see the question on the laptop.
Maybe that's other option, but you need to access to.
So
Yeah.
if I can't, so where is the option? Option is there, right? But we can't see the number.
Option is on the Kahoot screen,
Yeah.
but if you want to see the question and what the answer is for the option, you have to see the screen which is being shared on the Zoom screen.
Yeah, so we have two screens. You have, let's say, minimize this if you like this, and make it. Oh, sorry.
But we can't click there, right?
Sorry.
I was not able to click select.
No, because you need to click. You need to click. You need to click the Kahoot screen, not the Zoom screen. Zoom doesn't.
Of course, but that was also not working. I don't know what's it.
No, I'll show you, because this is the Kahoot screen. Can you see it?
Yeah.
So I can click on it, and then the other screen is the Zoom screen, which is the one that you need to put it on the side.
I've got it, so I've got the Zoom screen and my browser minimized. So they're both on screen at the same time, and it doesn't
Yeah.
matter which one I
Yeah.
click, they're both always visible. So I just figured that out now after.
But
Yeah.
at present, my screen should be like you, right? It doesn't. It's not like that.
Not like this.
Yeah.
The
His
Kahoot,
screen would be different because he is the one who is the
Host.
admin or something. Yeah, the host.
maybe that's right. Because I haven't tried to myself as a student. So what do you see from your side?
There is the option of quiz and times of something is there.
Everyone
Yeah.
seeing this? Luke and
Yes, sir, a bit different. Now we have like the feedback on our answer right now.
Yeah, correct or incorrect or.
Yeah.
you can see it like the one you can see now.
Yeah.
So you have these options, these colors, the red and
Yes, sir. We just have the options like red, blue, yellow, and green.
yeah. But you don't have the values?
No, the values we have to see on the Zoom screen.
Okay. Right.
Yeah, this was what the issue with
Yeah.
me.
But anyway, Nasruddin, you know how to use it now.
Yeah,
click,
it's fine now.
You click on the Kahoot screen and you find the question in Zoom screen. Yeah. Unfortunately, this is the only way we can do it. Okay, let's continue. All right. So next question. So now first we see who's the in lead, and then next question. What's the specific volume of water at 25? So it's same thing. You go to the same column, but find now specific volume of water, which is liquid VF. Yes. Okay, good. 4 we have. Right. So do you want me to explain this, or I think it's quite simple to know, right? So it's just go at the same temperature, 25, you go along the row. Under VF, you find what's the specific volume, which is this one, correct one. Okay. Right. So start the competition now. Okay, so next one. What's latent heat of evaporization? So same thing, 25, 60 here. Be careful. Go to 60. And he mentioned before, it's the HFG. Missed it?
Oh, I missed it too. Time was up.
Okay.
It's because of two screen.
You need to be quick, yeah.
Yeah, actually, I opened the table, then I couldn't come back to the Zoom screen.
Yeah.
At the right
That's
time.
why I'm telling you, it's better for you to have, when in the exam, better to have hard copy next to you. It's easy to go through it.
So is this like the exam will be like Kahoot based?
No, not Kahoot. No. But it's going to be online, of course. Going to be online, but you have 15, 20 minutes because it's 10 questions, something like this, but 10 questions, but it's multiple choice. You need to choose the right value.
So the quizzes are multiple choice questions.
Yes.
Oh, that's great.
You need to choose the right value.
So is this something from the table or you need to calculate as well?
Maybe some of them need to calculate because, for example, for the quality X, or the total.
Yeah, percentage of weight stream, something like
Yeah, I need to use the equation for the but it's simple equation, not complicated, but not like limited time for like this code. Okay. Okay, so what's happening here? Why it's not activating? Okay, let's see. Number 4. Saturated liquid enthalpy at 10. HF, remember.
Locked.
Locked.
You're a genius.
271. I can't do this. Like, I can't
Yeah.
get to my can't read the paper and then see the question and then get back to my thing in time. It's
Yeah,
like,
it's gonna be hard, I think so. Yeah, it's with one screen, it's very hard.
yeah, because even on your screen, the table is too small to read.
Yeah,
Like, can
Yeah,
you
like-
set
easier.
down timing, like time limit?
yeah.
Like,
maybe
I had the answer, but I just couldn't get back in time.
Yeah, that's fine as long as you know what to do. That's important thing. You know what to do, because this is like just interaction and preparing you for next week. But yeah, so if you know what to do, then that's fine. But if you don't know till now, please let me know, because this is like most likely what you need to do next week. Yeah. So, okay, no problem. Let's see, next one. So maybe if I increase, like, make it bigger screen. I don't know if you can see it bigger, or oh no, I can do it. I think. Let me check if I can do my screen bigger. Yeah, it's bigger. But maybe the question.
Yes,
yeah,
sir. I
maybe,
think, we won't be able to see the question.
maybe
quickly.
maybe we'll see the table clearly now. I think so.
We won't be able to see the options, I think.
Yeah, maybe. Yeah, let me check. Number 5. So now pressure 50 kilopascal. We need, what's the saturation?
What is the boiling temperature?
So that's the pressure. The first column is the pressure. The second column is the temperature. That is good. Yeah, 5 of you, it's
Yeah.
the right one. Yeah, good. Not bad. Okay, so this one, I think this one requires some calculation, so I made it longer. It's not 30 seconds, it's 1 minute.
So that's average of those.
Yeah, so you need to use this equation. Can't see it. Oh yeah, maybe you need to use this equation. If you write it down, write down this equation, and also this one. Oh, no, sorry, this one. Yeah, this one. This one, X quality is mg over mt, and where is that? Oh yeah, here one. Yeah. Oh, sorry. Oh. Can I show you how to find the total enthalpy and total? Looks weird. Where did it go? Anyway, it's not there. Okay, I didn't give you this yet. All right, no problem. So we'll leave this. We'll go back to the question. Right. So we'll go to the next one. Okay. Number 6. what's the change in specific volume? So VF minus VG minus VF at kilopascal, 100 kilopascal. So VG minus VF at 100 kilopascal. So go to the 100 kilopascal. Or you can take this.
No.
Yeah, you can take the VFG from the table, or you can do this. Because VFG is the difference between the specific volume of the gas minus specific volume of the liquid. Yeah, but you need to maybe more practice at home. Okay. So
that's that one's a bit unfair.
Hard.
It's like with the time pressure, I'm looking at the decimal places, and I was like, oh, that'll be it. And there was one different.
Yeah.
30 seconds per question. Come on, sir.
Yeah. because of the time concern, we need to finish the lecture.
Yeah.
Yeah, no problem. What's the internal energy of saturated water at 20? Internal energy, UF.
Internal energy.
Just UF. Yeah. Right. Good. Maybe next week I'll make it 1 minute at least. Okay, number 3. Haihu and Akibul. First, Imad.
Mad. Well done.
Well done. Okay, no problem. But well done for everyone, because thank you for doing this. It's really good practice for everyone. At least now you know how to use the tables. It doesn't matter like you choose the wrong numbers now, because I know that it's very stressful and very small time. But if you know how to reach the information, that's all I need from you now. But if you still don't know how to find the values, please let me know. I can stay after the class and show you again, right? Okay. Okay, so let's then go back to the class, to the slides. Now we have only 20 minutes, very short time. Okay, no problem. At least we cover the quiz part, and also next week, because you're gonna have tutorial, so you will do more practice on this. The tutorial, after you finish the tutorial, we will do the quiz. So at the end of the tutorial, you do the quiz. So you'll have enough information. Okay, so now this question actually relates to the tables as well. So we have mass of 200 grams of saturated liquid water. So now we know the mass. Okay, the best thing when you solve any question in general, in engineering or now in thermodynamics or heat transfer, you put all the information in front of you. So what I mean that I say, like here, M is, for example, M is 200. I know this gram, and then I say pressure, saturated liquid. So this means that, what does it mean that saturated liquid completely vaporized? So when they say saturated liquid, means this pressure is saturation pressure. So I know that P saturation is 100 kilopascal. Okay, so do it this way. Just put all the data somewhere on your sheet, and then start to do the calculation or do the answer, search for them. So for example, the first one here, the volume change during the vaporization. So means that we have liquid and then we change it completely to vapor, which means that I was somewhere here, VF, and we give, like we provided heat, we change it from VF to VG. Okay, so now we know that, we need to know what's the difference, VFG. So what do you think? What we should do?
X times VFG.
Yeah, at this pressure, we go to the pressure table, correct? Because we have pressure now, we don't go to the temperature table, we go to the pressure table, which is table number 5. Correct? So table number 5 is pressure table. So at this pressure, I need to find what's VF and what's VG. Or I can find maybe, because some of the tables, they give you VFG. So we have 3 columns, one for VF, one for VG, VFG, and one for VG, right? So if it's done, so we can immediately take this number and find out what's the VFG, or which is change of volume. But this is specific volume, not volume. If I multiply this by mass, which is 200 given in the question, multiplied by m, then I can get change in volume, because VFG is in cubic meter per kilogram, and the mass in kilogram. Then I can find what's the volume change, cubic meter, right? Any question? Clear? So let's do it step by step here quickly. So that's actually where to find the values in table A5. And as we said, either you find it from difference, VG minus VF, or you can get it directly from the table, get this value from the table if it's available. Okay, but this is specific volume. You need to multiply this by the mass. So we have 200 gram, we need to change it to gram, kilogram, divide by 1,000. So we have 0.2 kilogram multiplied by this value. We get volume change. Clear? Any question up to
No,
this
sir.
stage?
No,
Yeah.
sir, no.
Okay. And then second requirement, the amount of energy transferred to the water, which is latent heat, correct? And what's the latent heat in the table? You remember from the Kahoot? Latent heat is HFG. So if you find HFG, this is per kilogram. If I multiply it by M, I will get the total amount of heat required for this change. Yeah?
Yep.
Okay. So that's the amount of heat required to be supplied to the water, change it from liquid to vapor. Okay. Another example here. So in this example, we have a rigid tank. And when you see rigid tank, means the volume doesn't change. Like a container here, closed container. So the total volume would not change. So you know that this is the first thing that you found from the content of from the example itself. And the tank contains 100 kilogram of water. We also know that the total amount of water, M total, is 10 kilogram. What else? And at 90 Celsius, I know that temperature, still I don't know whether this is T saturation or not. I need to make sure, because it doesn't mean that when they give you temperature, mean that saturation temperature probably is below, maybe probably higher. We need to find out first, because there is no indication to the pressure as well. So if I know the pressure, I can tell that this is, I go to the tables and find out whether this is saturation or not. But now we have only temperature T90. I don't know, I need to check whether this is saturation or not. If I have two-phase region, then this is saturation, definitely. If not two-phase region, then this is not saturation. Okay, now you can tell now from the second statement, second sentence, 8 kilogram of the water liquid. What does it mean here?
So it is in the two-phase.
Yes, correct. Because 8 kilogram MF, 8 kilogram. So what's mg?
2.
Correct.
Kilogram, yeah.
Yeah. So now I know it's two-phase region. Then this is saturation then. T is saturation. Correct? Because it's telling me that part of it is water, not all of it. So that means that it's two-phase region. Okay, so now they need to know the pressure in the tank. So the pressure in the tank, if this is T saturation, if T is equal to C saturation and is equal to 90, then if I go to the tables at this temperature, what should I find in the second column?
70.183.
Yeah, but what the second column represents? Pressure.
Saturated pressure.
Correct. The first column we said, first column is T saturation, and the second column is P saturation. So if I go to tables, I find at 90, I just go and read whatever here. This will give me the saturation pressure. Okay? Clear?
Yeah.
Okay. So let's show you more details here. Now it's already done. So because we know that here, as you can see, pressure at 90 Celsius from the tables, you can find out from table 4, because saturation temperature, I can find next to that temperature what the pressure, which represents the saturation pressure. Okay.
So the value is slightly different than what we have in the table.
What you have there?
We have 70.18
Yeah, I told you, because for example, these questions, especially from the book, they use software. We call it EES, engineering equation solver.
Mm-hmm.
So this software has database of tables, and when you enter, let's say they give input, for example, the temperature, it will go and search what for the pressure from the database they have, and then it will give you the result like this number. So you'll find, like, between your table and the values in the book, some small minor changes. Like, as I said, if it's 70, you said 70.18.
Yeah.
Yeah. So you can see, like, second digit
Mm-hmm.
which is, like, not very effective, especially if you have, for example, here you multiply by 10. So show me what's the total here. So do you have VF and VG? What's the value of VF, VG you have?
So we have to add it together. Okay, just give me a moment.
No, no, you can,
Oh,
no,
you
no.
mean the individual amount?
Yeah,
Okay, for VF it's 0.0010 something. Yeah.
1036
And
or
36, yeah, 36,
yeah,
exactly
see?
what it says here.
And for the VG,
For the VG, it's 2.35 something.
2.35,
Yep.
really? So he 5.
359, yeah.
Okay, multiply by 2 and then multiply. So see what's the end, the result. If you can do it,
Yep, sure.
if it's easy for you now, you can do it, please.
I got 4.726.
Yeah, so 4.726, which is like, it's very close to each other. It's not big difference.
Yeah.
Yeah.
Makes sense, yeah.
Okay. Okay. All right. So we'll, this is actually the volume of the tank. Okay. We know that because it's rigid, part of it, part of fluid, liquid, and the other part is gas. So because it's rigid, it's contained in one space, then if we know the volume of the liquid, we add to it volume of the gas, then the total volume will be the volume of the tank. Okay. Any question? That's one actually. Still have 5 minutes. Okay. Do you have a class after this?
For
No,
me,
sir,
I
no
don't
for me.
know.
Anyone has a class after this? Yeah. Okay, no problem. We'll do it, finish it by the time. So this is, there is other way. This is like one way to do it, to find the volume of the tank. You take it individually, take the volume of each liquid and gas, multiply by the mass of each one of them and find out the total. You can do it other way around. You can find the total specific volume by using the quality. You remember we said V average is equal to VF plus X VFG, right? So we can get VFG from tables at 90 Celsius, and we can get VF from tables as well at 90 Celsius. And if we know X, what's X? We need to find X.
X is, I think it's the vapor.
Correct, on the
Divided
total.
by the total, yeah.
So the vapor is, we said 0.2 kilogram.
0.2 divided by 10.
No, sorry,
Wait,
2 kilogram. Yeah.
It's in kg, yeah.
Yeah, 2 kilogram.
Divided by 10, so 0.2, just X
Yeah.
is 0.2.
Correct. So the X then, yeah. So that you can find X. Now, all these values can be found, then it's easy to find the average. Now, if I know the average, which is the two-phase volume, multiplied by the mass, I can find the tank volume. So this is another way to find the tank volume. It's up to you which one you use, but both of them should give you the same result. Okay, so you can see here, both of them have the same result, 4.73. Right. And we said that not only for water, for any pure substance, you will find the tables available like this. So this is one of the substance that we're going to use in some of our examples, which is the refrigerant 134A. Refrigerant 134A is used widely in air conditioning systems and refrigerations as well. And this is like, environment friendly substance, because before they used to use the different substance which affects the ozone, call it Furion. So they banned this substance, and since maybe more than 15 years or and they start to use 134A, which is as we said, environment friendly substance. So you can see that the table structure the same, but we have also the first, say, column pressure table, or temperature table. Same thing, you go along the pressure, you find the temperature next to each pressure, and then you find all the other properties in that row. Okay, so if you have an example with this type of refrigerant 134A, you can simply go, and this is table actually table A12. You can download it if you like later on. Okay. Any question? All right, let's see this example. We have same thing, 80-liter vessel. It has 4 kilograms of refrigerant 134A, and you have pressure 160. Okay, it doesn't tell us whether there is a mass of liquid or mass of vapor, nothing. I only know that the volume, total volume, is given 80 liter, but make sure that this is liter, not meter, cubic meter. And we know the mass of the refrigerant. So the refrigerant here means total mass, because we don't know whether it's liquid or two-phase. We're going to put empty now. So the total mass is 4 kilograms. And the pressure, P, I don't know whether this is saturation or not saturation, below or or above saturation. But I will put it here as 160 kilopascal, and I will check later on. So what you can do here, because you don't have any indication about whether it's two-phase or single-phase, you can find average, V average. How to find V average? If you have the mass and you have the volume, the V is cubic meter per kilogram. So I divide the volume by the mass, I can get specific volume average. And I take this average and go to tables at this pressure. And in the tables, for example, this is the P line. Next to the P line, there is a T. And then, for example, after U, there is VF, there is VFG, and there is VG. These columns. So for example, I take 160, I go and see, I don't check now the temperature, leave it now. I go to these two values, VF and VG, and compare my value, V average. If it's falling between these two values, then I am in the two-phase region, correct?
Yep.
And this was what you're going to find now very soon. So if it's there, then the pressure, it's P saturation pressure, and the temperature, I can find it easily because next to it is the temperature, and all other values I can find it because now it's in the two-phase region. Okay? Understand this, everyone?
Mm-hmm.
Probably if you go to the detailed here in the question, you will find it more. But first of all, as we said, we'll find the average. And if I take this value, I go to the tables, and you'll find this value between VF and VG. So can you see here? VF is lower than V average, and VG is higher than V average. And this is from table A12. Okay, so which means that it's two-phase So from that, I know that this pressure now it's P saturation, and the temperature next to it is saturation temperature. Okay, so this is saturation temperature at the pressure, specified pressure, and then you do other values, find other requirements. All right. You can find X value because remember quality, we said V average is equal to VF plus X VFG. So if I know VF from tables already known, and VFG already difference between these two, correct? V average, I found it from the top here. So the only unknown is the X. I can solve this question, this equation for the X and find the value of X, which is 0.158. Okay. Clear?
Yep.
Okay, so any question? So that's actually, and also of course you can find the other values for H average, because this is H average of two-phase flow. You need to find from the tables HF and also from table HFG. You know now X is already found from the last step. Easily substitute them in this equation and you get the enthalpy of the two-phase flow. Okay. The last one here is to find the mass of gas, mass of fluid. It's quite easy. Once you know the X value, you multiply it by the total, because X, we said X represents the quality, which is the amount of the percentage of vapor in the total. If you know the percentage, you multiply by total, you get the vapor mass. Yeah. So what I need from you actually, just try to go through these questions, please, at home, because these are really quite important for your quiz. Try to practice these, and it's really very easy. I know that now because of the time and you don't have proper access to the tables, but once you have the tables on the next to you, hard copy or put it somewhere on your screen, it will be easy for you to understand this, believe me. Okay, any question before we finish? Because I will leave this part for next week. This
So
is not,
for the quiz, how many questions we will have?
it's 10 questions, but as I said, it's multiple choice.
All of them multiple choices?
Yeah, all of them. But some of
Next
them,
week, yeah.
yeah, next week.
Next
In
week.
the quiz time. I will send you anyway a reminder, send you an email. But just to let you know that you need also, let's say I said, tables, and also need a calculator next to you and a pen, of course, and scrap
So
paper.
It's gonna be on tutorial class, right?
Yeah, yes.
Okay, so the tables and everything should be printed out with
It's
us?
up to you. I told you, it's easier for you to print it out, but if you can manage yourself, that's up to you. It's all
Just the
totally.
A4 and A5 stuff? Or?
No, because what happens, you will not write, it's not written exam. It's
No, he's asking if we only need the table 4 and 5.
Which tables do we need?
sorry, I thought you did mean A4 or yeah, the size of paper. No, it's A4 and A5.
Okay, no, because there was a question of the refrigerant, so I was confused.
Yeah, but you need to
table.
know, you need this in your tutorial anyway, refrigerant. But you don't have to print the refrigerant, just print now the water tables.
Just A4 and A5. Okay, thank you. Sir.
Okay. Okay, any other question?
No, that's
Something
it.
in the chat box? Oh, okay, nothing here. Right.
See you next week again, sir. Thank you.
Okay, then. Thank you, guys.
Thank
See you
you.
next week. Good luck.
Bye.
Bye.
See you, sir. Bye.
Bye.